Welcome. My name is Stephan Loftus-Mercer. Some of you know me on the forums as AristosQ, whether on Lava or ni.com. I'm a principal software architect with LabVIEW R&D at National Instruments. I've been there for about 22 years. I have my fingerprints on just about anything having to do with the block diagram. As the lead designer for the OO features of LabVIEW. And today, I want to talk to you about a new part of LabVIEW, LabVIEW Interfaces. LabVIEW Interfaces are brand new as of LabVIEW 2020. Thanks, COVID. So, I've not had a chance to actually present this to the NI Week audience and to get this out there. Some of you may have seen the presentations that we did online. I had the option, the benefit, the blessing to be the first person to have to figure out at NI how to present on a topic to a completely virtual audience back in April of 2020. And so that's available. We've done a couple of other presentations, but this is the first time I've really been able to talk about this in person. The earlier presentations on interfaces are available online. You can find the introduction to G interfaces up on in LabVIEW 2020 up on YouTube. And you can find the presentation that I did for the earlier GLA summit with John McBee on the LabVIEW Wiki video. These two presentations are essentially a lot of the same content as what you'll see today. My goal every time I present this is to try and present it in a slightly different manner with a slightly different spin on how I'm teaching it, because different people absorb this material in different ways. And the other two conversations were either a very heavy academic slant on the very first one of this is the philosophical conceptual aspect of interfaces and I'm just simply laying it out for the LabVIEW community to discover how to go with it. And the second one was a very specific case study that delved deep on the technical aspects of how we used LabVIEW interfaces in one particular programming environment. What I'm going to try today is a much more generic example, working from a test and measurement like sort of thing, and allow you to kind of see maybe how these things work in one particular venue. So if today doesn't quite sell you on interfaces, maybe look back at some of the others, because I'm trying to make sure that the whole community really gets the value of them. In general, if you're building a large-scale application in LabVIEW, you should already be using LabVIEW classes. We know for thousands of studies and lots of user feedback that development of applications is generally more scalable, modular, all of the different advantages of good software when you can do object-oriented designs and break things down and keep things organized. Interfaces, as we can see in most of the other major OO programming languages in the world today, bring a whole new level of power. They're not a complex concept. As you're going to see, this presentation doesn't have giant depth the way the very first OO presentations did when I was trying to bring the whole community across to a new whole paradigm. It's a very simple modification, but it has big ramifications and they get used in a lot of places. So when I say it's a very simple modification, mentally, you can get a lot of distance out of this one sentence. An interface is a class without a private data control. So there we see a class, and we get rid of the private data control, and we change the little bit of the icon, and boom, now it's an interface. That's all it took. You're wondering why, if that's all it took us 15 years to program the darn thing. There's a lot going on behind the scenes to make all of the things work. And what it is, once you get rid of that data, that's what we're going to look at today. Now, some of you may remember when we first introduced LabVIEW classes, we talked about a class is a glorified cluster. You take a cluster and you lock its data so that most people can't see it. And you take away all of the ability to use the information in there. And everyone's like, why do I want a damaged class, one that is less useful? And we had lots of presentations on why the limitations on data made a better program, because now you could, like security, you could verify which parts of your program were modifying that data. Well, in much the same way that we have to adjust, we're going to take this idea of a class that just can't store data, and we're going to use it to achieve more power and more control over our application. So, interfaces are stateless types. They're a new data type, just like a class, but they are stateless. They do not have internal data that you can carry along. They don't define what's in there. Instead, you can add methods to them, and they define behaviors. That's all that the interface is able to do. Just, here's a list of behaviors. That's mostly it. If I stopped my presentation at this point, you could walk away saying, I know what an interface is, and I generally could create one in LabVIEW, and you'd kind of be like, okay, well, but why would I ever do that? And that's what we want to do. So if you only get this part, at least you've now got the what of what they are, and that should take away some of the fear I've heard in the community over the last couple of days in talking to people of, well, they seem like a really complex topic. I'm like, no. That's, as far as what they are, that's it. So that's first level fear. Now we're going to keep going. So what we want to do is talk about how do we differentiate a class from an interface? Where do they differ? Where are they the same? And see why this getting rid of state serves a value. So the first thing I want to note is they have the same file extension, but they have a slightly different icon. If you ever looked at a class icon, it's actually two icons put together. The banner comes from the class file. You go into the class, you edit the properties, you set this is the banner that's going to appear on all of my methods. And the bottom section comes from the private data control. Well, an interface doesn't have a private data control, so its icon is somewhat reduced. The reason for the same file extension and the reason for keeping things as nearly identical as we possibly could is because from a user point of view, these are the same thing. When someone is not an author of a class or an interface, they see a type in the palettes. It's got a constant they can drop, a control they can drop, and a bunch of methods. From their point of view, they're just using a new data type. And we want that because your CLD level folks that are downstream of the architects who are building reusable libraries and everything else, they're just using these types. And from their point of view, there's no difference. They see a class, they see an interface, it's the same thing. They drop it, they wire up some methods, they make some calls, and they're happy. The power is on the person who's developing these new types and is creating new extensible libraries and is creating shims across their hierarchies that can be used in new and innovative ways. So we constantly, in the development of them, we're like, when can we cleave close and when do we have to push away? So we have a very subtle difference in the iconography that allows you to look at them and go, I know that's an interface, but anybody who's not really paying attention, it just looks like a class. I can replace a class with an interface because I just save over it, I create a new interface, overwrite the file, now it's an interface. All the inheritance comes for free. So let's talk more about the inheritance, because this is where the magic starts to happen. This is a basic class tree. You have LabVIEW object. LabVIEW object is always the root. It's a useful placeholder. There's some generic operations. It's nice to have up there from time to time. We have a grandparent class, inherits a child class. They always form a tree. Everybody comes down. And LabVIEW doesn't have what's called multiple inheritance. You can't have these classes have multiple parents. You can't have two different data blocks that you try to bring together. Anybody who's tried to use C++, C++ supports multiple inheritance. It's one of the first big OO programming languages that really became popular. And it has multiple inheritance. And modern C++ textbooks all say, never use this feature. Just pretend it doesn't exist. And it's because the world slowly learned that trying to bring chunks of data together resulted in the inability to maintain the promises of a class. Everybody who writes a class, the methods make promises. You call this method, it will transform from state A to state B. or it's read-only and it won't change state, or whatever the rules are for that particular method. And when you inherit a child class, it inherits all the promises of its parent. It's allowed to make deeper promises, more promises, change fewer things, narrower scope, but it has to keep all the promises of the parent. That's the basic Liskov substitution principle that we've talked about at various NI weeks in the past. But bringing these blocks of data together results in the inability to do it because you can't always keep them up to date. You get some weird diamond patterns in the inheritance tree. It's really hard to design good software where there's multiple parents defining what the correct behavior of state is. It's hard enough to the point that it's so error-prone that the industry basically said, no, don't do it. Then along, in my experience, so apparently this is, I didn't know it at the time, but apparently this is an older idea. But in my experience, we'd all figured out that multiple inheritance was bad. And then James Gosling invented Java. And he gave a presentation that caught my attention years and years ago on interfaces and a better way to do it. If we get rid of the state, we could support multiple inheritance. We could tie these things together. And so that was inspirational to me, and it's one of those things that has sat in my head about how would I bring this power to LabVIEW. Well, so here we go. When you create an interface, interfaces inherit from LabVIEW object because the objects that are actually going to be on that wire, they're objects. They're instances of some specific type. But they don't have any data to them, ever. So then they're always going to inherit from the only class they can ever inherit from is LabVIEW object, because it also is guaranteed not to have any data. Classes then can inherit from an interface. In fact, they can have one class parent and as many interface parents as you want. So we can introduce some more, and that parent class now has 3 parents. It's got one that brings it data, and 2 that just bring it behaviors. The movable class, that's another interface. It's allowed to inherit from other interfaces. It has to maintain that 0 data promise. Not just 0 data now, but 0 data permanently and for all time. That's why it can't, even if a class has no data itself, you can't inherit an interface from it, because it might change that promise in the future. So interfaces always inherit either from themselves or from LabVIEW object directly. And they form not a tree, but a diamond graph coming down. This ability to bring things together means that I can have a parent class that can be a grandparent, it can be a widget, it can be an operator, it can be whatever I want to bring to it, and allows it to play multiple roles in the system. When we're talking about classes, historically, you would define a class for some library and say, I'm going to take data that is of this parent class and I can do operations on it. And then all of your callers out in the world would create children classes that have specific behaviors and that fill in the holes in the algorithm with dynamic dispatch behaviors to say, when this object goes through, here's the specific override that I want you to do. Interfaces are exactly the same. You're going to write some set of VIs that take an interface object, and they've got some dynamic dispatch methods, and the overrides are going to fill in the details of the behavior for the object on that wire. It's exactly the same rules. The trick is that because you've got an interface, you can have one object that represents some complex stateful thing in your system, like a full-fledged piece of hardware that can do lots of different operations. And it can fulfill all these different roles in your application and not have to step on itself and not be overloaded. And you can be very clear which libraries operate on which behaviors, where are your dependencies, and what are you tracking. There we go. So a class, so the last piece of the inheritance is you can get some really weird diamond trees filling in with, kid actually inherits twice from widget through different paths and all of this. Those complex things are very rarely used, but they're useful. And I'm not going to get into the details of why they're useful today. That is beyond the scope of what I want to try and do in an intro piece like this. But be aware, you can create some very intricate inheritance trees and bring these behaviors along, and they don't step on each other. That's a completely legal implementation tree. So class gets one class parent and infinite interface parents. And an interface always gets LabVIEW object and infinite interface parents. Now I want to throw one piece of vocabulary in here, just so you're aware. National Instruments, me, made a conscious choice. In a lot of other industry language, you're going to hear that classes inherit, classes implement interfaces. They don't inherit interfaces, they implement. And so if you look Google and everything, you're going to see that terminology. That terminology is actually changing in industry because LabVIEW classes have default methods. And we're going to talk about that a little bit more. You actually inherit behaviors down that are already well defined instead of just being empty methods. The other languages, C#, C#8, or Java 8, C#'s latest revision, I forget the number, they've all started adding the same capacity. And when we start talking about, well, what do we get? They're kind of having to pick up the language of inheritance. So if you think LabVIEW is a little out of step with some of the stuff you'll read online at this time, it's my personal bet that the industry is shifting in our direction because we've got some features that they were getting at the same time. All right, why would you use interfaces? Now, at this point, in a CS lecture or something, I'm going to duck into a bunch of vocabulary terms, and each one of these is an hour-long lecture. And any of you who are going to be architects in the room, you should get to know these things. Find training course materials, understand what these terms are. But I don't want to get into that today. I've delved into some of that in other presentations and white papers and documents. Today I want to try and focus on one small use case to actually see if I can break through some of the hesitation around them. So I'm going to move past the vocabulary words. I have written a simple test executive. This comes with a warning. It's a very important warning. There are plenty of good test executives in the world. Please, please, do not write your own test executive.
Just go buy one.
In fact, go buy Test Stand. This slide brought to you by Yanai Marketing. There are times when you have to write your own test executive. I helped one company put their own together not too long ago. It does crop up from time to time that your use case is so specialized that you warrant that. But by and large, it's not a good idea. However, I know that most of this room has spent some time developing or maintaining a company's specific test executive, or has written extensions that are your test executive specific. And therefore, this makes a good small sample use case that I can talk about where I'm pretty confident everyone in the room knows all the moving parts without me having to get into all of the details of what each individual class does. So I have written a simple test executive. My simple test executive has 4 parts. It has a configuration class. That's going to be the thing that read some config off disk, build an object that is essentially a property bag, name maps to value, name maps to value, name maps to value, that is going to somehow configure. I have a class that represents a device, a thing that I want to test, that I need to operate, that I need to do something with. I have a test case. This represents a set of inputs to the device and an expected result, and can do the evaluation to see does this test case pass or fail. And I have a test result. Test case produces a test result, and that test result then can be used to archive what happened during that test, not just did it fail, but why did it fail, what were the current conditions, was it raining that day, et cetera, et cetera. This one is made to write into log files and such. I then start with this basics, and I created some specific extensions. I have an oscilloscope class. And this is a benchtop instrument that is going to be able to, I can give it different types of stimulus. I can see whether it gets the right picture on the screen. I have test cases that are specifically, I'm going to specifically test the waveforms that are appearing on the screen. And each waveform test case produces a waveform result. And so this is my general framework, and I've coded it up, and it works. here is my very simple test executive to run. I initialize so I have a configuration that I get, and I initialize my oscilloscope. Great, there we go, there's my oscilloscope. Oh, I should mention, these 3 classes, I gave them blue wires. The others, they all have the standard object wires. So I initialize the oscilloscope. I load a bunch of waveform test cases. How do I load them? Oh, I don't know. Load them from disk, read them from a database, create them on the fly. Maybe it's a stored concept. Somehow I get an array of test cases. And I get an array of previous results. So the last time I ran this, maybe it's it's got population, so I don't have to worry about an empty array, special cases, just bear with me. But for whatever reason, this is what we saw from those test cases the last time they ran. So I can get that, I can see the test cases, and here we go. What do? We're going to run the for loop. Each time we're going to run the test. It's going to somehow update the state of the oscilloscope, because each test case maybe does something stateful to the oscilloscope. It's not necessarily good test case design, but sometimes it's necessary, so we'll go with it. Run test then produces an output that is some actual test result. Great. We're going to check whether or not that test result passed or failed. If it failed, then we're going to get what was the previous, and we're going to update our different arrays. So the top array is just all of the test results. There you go, all the test results. This is the repeat failures. So these are the ones that they failed last time, they failed this time, it's no change. If you've made a change to your commit code, it's not your fault, somebody else broke it earlier. These are the new failures. If you made a local change, it's your fault. Very basic set of code. Useful, we've probably all written something generally like this at some point. Because you end up in these comparative type situations on a regular basis. I can take this code and go into any number of companies with this simple a hierarchy and solve a whole bunch of test bench cases for small startups. All right, time goes by, things are working, and then we decide we get a test that's failing and we can't figure out why. And we're like looking at it and we're like, is it the test that's written wrong? Is it the oscilloscope is giving us bad data? What? I need more information. And so we drop a probe. And now in LabVIEW 2022, when you drop a probe, they bounce. No. Hey, rubberized probes. I mean, I don't know how many you've dropped a probe. They shatter all over the floor, data leaking everywhere. It's really a serious problem in the industry, but we're working on it. So you drop a probe, and there it is. And you're like, yeah, I can see that it's amplitude, frequency, not exactly, it's not the form I really want to be able to look at these things in. And it's worse if I need to drop a subsequent probe, and actually look at the oscilloscope. Because the oscilloscope has got all my configuration stored off, which is this map. You should all be using maps. Keys to values, that's stored as a variant, and then I've got the sampling rate down here that is the child class data. There's a lot of noise in there, and I still don't really see how the relationship between these two works. What I'd really like to see is I'd like to look at the oscilloscope as a waveform, like what is the actual waveform on the darn thing, and I'd like to look at the test case as what's the expected waveform. And I'm looking at it, I'm like, okay, I'm going to write some custom probe, and I'm going to write it one-off. And there's a bunch of debug techniques that we have for this. But today I decide, actually, you know what? This comes up often enough, and maybe I should make it a proper part of my user interface, because then we don't have to do special code in the future, and people don't have to figure out how to debug it. So I'm going to take the time, and I'm going to add some new functionality to my whole system. So I come back to my hierarchy, and I say, okay, I'm going to create a new interface called Waveform Coercible. You will find that most of your interfaces end in able or It is either a thing that does something, the marketer, the deliverer, the whatever, or they're a thing that gets done to. The coercible, the loadable, the whatever. Interfaces are typically named for the ability and the behavior that they bring to the system. So they're a role in the system. And if you've ever listened in English to a lot of roles, performer, dancer, all these things, there's a lot of terms. And then the other type of role is things get done. And able is pretty common. So there's a lot of the things that get named that way. a word about naming. In most of the text programming languages, interfaces get named with a capital I at the beginning of their name. And when I've surveyed C# programmers and C++ programmers, the I is mostly in the way. It gets in the way of a number of refactoring things where they now have to rename stuff to either add the I or get rid of the I and yada, yada, yada. And most of them have told me that they really wish the I wasn't there, but they're all keeping it because it's industry standard and they've all got the I. And if they stopped using the I on one library, everyone would be confused. And they're right. And it doesn't make any sense to get rid of it because that's kind of your clue. They also don't have a visual indicator that this is an interface. Well, guess what? We're a graphical language. That little bit of iconography difference, that little symbol difference in the project tree, we know it's an interface. We can see that. I can even spell out the word interface in the context help window. We don't have quite the same recognition problem, and we don't have the same history of always having used the I, so don't use the I. There's no reason. We don't have to type the name. We drop things from palettes. So I don't have eyes. I mean, I have eyes, but I don't have eyes on this. So I created Waveform Coercible, and I gave it a method to waveform. So all I really need is I need the ability to coerce these things to waveform. And I'm going to make these three classes able to coerce directly to a waveform. All they're going to do is they're going to inherit from it and then override, how do I get a waveform out of this structure? So the oscilloscope, here's your instructions for getting a waveform out. Your waveform test case, here's the expected data. Let me load that as a waveform. Your waveform result, here's what happened. Here, let me load that. Great. So now I can coerce all of these over to waveforms. So now, having set this inheritance up, I'm going to write an XControl. I know you should all be using Q controls. They've got a number of advantages and everything, but not everybody knows what a Q control is, because not everybody has been reading the Lava forums and going, wow, these are really awesome. And now you all go because I've mentioned them. But the XControls are really nice. They're built into the product. They have a lot of advantages, and you can use them. And they make nice demo for right now. So I wrote an XControl, and I gave it a front panel, so it's a nice plot, and it can show a bunch of graphs. And I gave it a data that is an array of my Waveform Coercible interfaces. So I can have an array of waveform coercibles, wire it directly to the FP terminal for the XControl, and it will display that data. Great. All right. So nice and simple thing. Now that means I can come back to my simple test executive, and I can do this. I can take the oscilloscope and the test case, do a build array, and wire it straight into the multi-wave XControl. What happened at that build array? Well, the same thing that always happens when you wire two classes to a build array. It found the common parent and made that the output. Used to be, the only common parent between those would have been LabVIEW object. You can't do much with LabVIEW object. I mean, it's useful for some things, like when you're playing with variants or doing flattened to data or stuff like that. But for the most part, it doesn't have a lot of methods. It's got comparison and flatten. But now, LabVIEW looked at it and said, wait, there's a better parent to pick. And there's some fairly complex logic that goes into picking which one goes in here. And I'll leave you to read the documentation on that. But suffice it to say, it mostly works out of the box. If it can find a least common parent, a lowest common parent, that's what it's going to go to. And in this case, it just says, hey, both of these can go to Waveform Coercible. So the output array, without a need to rewrite the objects at all, is an array of Waveform Coercible, and I can wire that directly to my XControl. In this particular case, that XControl represents a reusable library. And it says, I can act on anything that you can make into a Waveform Coercible. And I taught these classes how to be Waveform Coercible. So I can just plop them together. Now, this is a little contrived. I've obviously, this is working code. I had this all available, but it's not exactly a day-to-day test scenario that you're necessarily involved in, but it gives you, I hope, a little bit of an inspiration when you're looking at, I have disparate objects that are each fulfilling different roles in my system, but they've got this commonality between them, and I'd like to write one library that I can pass all of them into. And I'd like to be able to funnel them all through a common interface. That, when you find yourself using that phrase, common interface, think to yourself, maybe that is an actual interface. And it's one of your big clues was when you're just talking out loud, you're like, oh, I'm using the vocabulary. Maybe I should use the thing that matches the vocabulary. Maybe LabVIEW should add that feature. That's what my thought for the last several years. And then you can do things like this. You can build loggers that can take any of your objects and log them. You can build, things that will take different types of hardware that all have a temperature ability, and you just have, this one is read temperature, but you've got weird-ass devices that are all capable of reading temperature because somebody built a hard drive that happens to have a temperature sensor on it, and you happen to be able to use it to read the temperature of your CPU. Don't ask. Yes, I actually encountered a customer using it that way. And you're like, your hard drive class is your temperature sensor. Great. So, we do find ourselves in weird scenarios, in weird cases. Interfaces are there to help you segregate this behavior, this behavior, this behavior. This routes into this part of the program, this goes into this part of the program, this goes into this part of the program. And now I can have the functionality of my classes. They can define their local state, and they can fill in, when I get this behavior, here's how my state transforms, and be consistent across it, and still reuse all of these reusable pieces because they can all dispatch and talk to stuff. That's the theory anyway. I'm hoping it bears out in practice.
So this, especially when you put it, kind of looks like a malleable VI.
It does.
As like a simplified version of what interfaces are doing. So you can talk to like when you might choose between a malleable simple thing and a more interface.
Yeah. So in fact, when I introduced malleable VIs a few years ago, I described them as a poor man's interface, especially for their ability to coerce on the class methods, because they'll simply they'll look at a class, analyze it, and find any matching name and call that version. Interfaces are far more flexible for tying different types together. And so the malleable VI is basically one linear dispatch case when you're just going to go do that. But it's hard to get information out of the malleable VIs and maintain that statefulness across. And what you'll find over time is that as you create hierarchies of interfaces, you can't really do that with malleable VIs, where you can say, this is a group of functionality altogether, and I need all 4 of these to be defined in order for the type to be well defined. If I have a malleable VI, I really only have one method that I can plug in and know that I have defined it well in my class. And maybe I document, you need to implement these 3 methods. But it's harder. With the interface, you're like, I implement this, and I get a must override requirement. These are the 3 things I need for this interface to work. So they're much more tied to the language to give feedback to your downstream developers about what the requirements are. They are much more extensible over time, and they can be independently used to actually segregate your development process and to create separate modules in a way that the malleables still tightly couple things together. So I realize it's a bit of a block there, but these are more powerful as the short way to do it. But you're right that one is similar to the other, but they were, back when I didn't think we were actually going to get interfaces, I spent some time making sure that malleables could fill a slice of that power.
This may be getting caught on your contrived example a little bit here, but if you're putting these into a plot, but they're dataless, how does that?
But they're not dataless. The data type said, I don't define data, but those are objects on the wire. Just like an upcast, they didn't lose the actual types on those objects going in is still test case and oscilloscope. They didn't lose their data just because they're traveling on the wire. The data type said, I don't define state, but I can carry objects that have state if they inherit from me. That's important. There, oh, good, I got some ahs. Good question. So that's not a loss of data when they go through that. That's just the same as any other upcast. When you go from a child and you put it onto a parent wire, it's still got the child identity. It still carries all of the child data along with it. Alan.
All an interface does is put a different handle on your object so you can drag it to different places.
Yeah.
And you use it in different things. But it's the same thing with just a different way to use it.
Yeah. One of the things I've actually not liked about LabVIEW is the presence of those coercion dots up there, because they make people think the object somehow got rewritten. But we've always had upcast coercion dots, but those are, I kind of wish those were a different color coercion dot, because they're not the same as like an integer being rewritten as a double. This just says, there was a type change here. It doesn't mean that the data necessarily got rewritten. And any upcast coercion dot, whether it's on a ref num or on an object, they don't mean the same thing. They don't, and they certainly don't carry the performance impact. The two more generic node, when you're going up, it's a no-op in an executing diagram. I saw another hand somewhere back there. No?
Sure. Just to clarify, so here we have two waveforms, one from load waveform and one from the test.
Yeah.
So what's happening there?
So we have two waveform, we have two objects that both have a two waveform method. Let's be very clear. So we have a test case object and we have an oscilloscope object, and they both have the ability to call to waveform and return a waveform. Well, the X node, let's see, can I go backwards? Yeah, so the XControl in the block diagram of this is simply on each of those objects calling to waveform and getting a waveform and putting it on the graph. That's all it's doing.
So it's both waveform.
Yeah. So you're not actually doing the construction here, it's doing it inside the XControl where it says, I know how to operate on those objects. All right, so let's go a little bit deeper. Interfaces can use most method options. I struggled with the title of this slide, so bear with me a bit. Basically, if you can do it in a class, for the most part, you can do it in an interface. But some of the starting points are a bit different. So, most of the time, when you write an interface, almost all of the methods are going to be public, because it's what makes most sense for an interface is you're generally creating a public interface for everybody to use and to reuse in various places. But you can have methods of any scope. Public, private, protected, community, they all work on LabVIEW interfaces. So there's not a limitation there, and there are good reasons why you're going to use that. We'll get to that here in a moment. Most methods on an interface will be dynamic dispatch. Unlike classes where you will frequently end up with a whole bunch of static methods, most of the time you're defining an interface because, I mean, they don't have any behavior most of the time. They're no-ops, they don't have state. All they're saying is, this ability exists. And so there's not many use cases for static dispatch methods on them. But there are a few use cases. And those few use cases are when I want to write a static dispatch method that all it does is call other dynamic dispatch methods. So I've got some operation that is a composite of other operations, then it makes sense to have static. So we allow static dispatch to be methods on the interface. The dynamic dispatch methods on an interface will default to must override. So when you create a class and you add a new dynamic dispatch VI to it, it defaults to no, you don't have to override this. Because most of the time in classes, you write the parent version and that's what you want. And it's at least common enough that a lot of the children won't necessarily override it. The parent defines some behavior, and if a child needs to override it, they can. And we go in and turn on must override when we want to say, this is an abstract method, you're going to have to give me a definition. With interfaces, there's no state there, there's no implementation that can really be filled in for the most part. So the default is must override. And trust me, you're going to find that's a lot more useful. So whenever you inherit from an interface, it's generally now go fill in all of these methods and check them off, because the default implementation doesn't do anything. But you can turn that option off as needed to create a default method. So sometimes I do want a default method. There are some cases where I can fill in the details because it uses some other parts of the interface, some other methods, and I can create this composite that's like, this is a compound operation. Most of the child classes don't need to override this. I'm going to turn off most override. As long as you override all the little inside pieces, you're fine. But methods cannot invoke the call parent class method node. And if you think about it, well, first of all, it's named call parent method a call parent class method. We renamed it in LabVIEW 2020 because now there's multiple parents. And if you think about it, if we went back here, if I try to do a call parent node inside one of these things, if I've got tons of different interfaces, it can be totally ambiguous which one did you intend to call. Because multiple interfaces can all define exactly the same method name. And they can all inherit, and you can bring them all together. Because there's no behavior to worry about. You have one override, and it overrides all of them. And it allows you to use it in all of those different contexts. But you can't do call parent method. So call parent is restricted only to the class parents. So if you try to do it for an interface method, you get that. So the one thing you can't do, the one thing that is just locked, is that interfaces always enable the restrictions on new and delete of data value references. There's some very complex technical reasons for that. Has to do with what we enable for the casting. Trust me, this is not us just skimping out on a feature. This is a good technical decision that keeps you out of some very weird fail cases that otherwise just wouldn't work. And so you're all used to the, because it defaults on that, new and delete are bound into the class. You can only do them as constructors or destructors of the class. With interfaces, that is always a requirement. You can't turn that off. And you're just going to have to trust me, for those of you who are advanced programmers that actually care about this case. I'm mentioning it just so that nobody is surprised. I'm pretty confident this is a good decision. But that's what you can generally do. Otherwise, they're like classes. Program them that way. Oops, go forward. Interfaces do not support the property node syntax. Sorry. Turns out property node syntax is really hard. There's some complexity because you're doing a bank shot through the name of the property to the actual implementation VI. Which interface is actually defining the property became actually quite hard to track. And there were a whole bunch of weird fail cases that we were going to have to develop compiler detect and everything. And we finally just punted on it. And we're like, no, we're not going to support properties on it. We could. This is one of those where this isn't a technical decision where it can't be done. This is one of those where we were like, I'm not sure there's enough value to warrant the R&D input. If there is enough value to warrant the R&D input, the community will say so. So if you really believe that that's an important thing, that's feedback to give to LabVIEW R&D and for pushing it in the future. But at the moment, it was a sufficiently complex lift for a sufficiently low buyback that we decided we're just going to leave that one aside.
Actually, it's not crucial, but convenient.
It's not crucial, but convenient. And we would like to have it. It's the cost-benefit analysis. All right, I'm just going to tell you. Prefer interfaces over abstract classes. Abstract class, up at the parent class, usually abstract classes don't have any data, which makes them pretty much like an interface. And you can throw a bunch of methods on them. You can mark them as must override. They serve a lot of the roles that interfaces have in the system. Why then would I say that you should prefer the interfaces? Well, the interfaces are a lot more flexible.
Is there an easy method to convert your existing code from abstract to interfaces?
No, there is not at this time. I would like there to be, repeating the question, is there an easy, convenient way to convert an abstract class into an interface or vice versa? No, not at this time. It is on the things we would like to have as the refactoring tools and is definitely in the backlog of things to worry about. The philosophical answer for why to prefer the interfaces is it's less of a temptation. If you're working with an abstract class, it has a private data control, and today you're not using it. And today you're really using it as an interface, and you're getting all this job done, but it has a private data control. And there's a temptation to say, on any given day, look, we could refactor this, we could create all of these different places. Let's just shove it into the private data control and be done. Let's give it some state and we can walk away. And then from thereafter, you can't use it as an interface and you start getting data dependencies and it changes the nature of the game. If you design it as an interface up front, that temptation is never there. And when you get to the place where your state, you do it the right way. So that's a philosophical answer. There's a practical answer, though, several of them. One, as we've seen, is the ability to apply across hierarchies. Because once I define an interface, it's not tied to one thing. And it doesn't mean when I inherit from this, that's all I get to inherit from. So I get much more reuse out of my interfaces than I will ever get out of my abstract classes. Two, that multiple inheritance. I can have a single object where I can bring many of these together. I can't unify a whole bunch of abstract classes. So I've got two different reasons from inheritance side to see more flexibility in an interface than an abstract class. The third one is this weird technical thing. An interface does not lock when simultaneously loaded onto multiple targets. This is known as Stephan's bug number 1 and the biggest mistake I've made in LabVIEW design. When you have a class and you load it on an RT target and on a desktop simultaneously, the class is locked and you cannot edit it. And this was a small thing I put into LabVIEW 8.2. This is shim while we figured out the technical problems and okay, we'll fix it someday. It is now so deeply embedded in the code, I don't know how to untangle it and to get it unlocked, and we've got specs and it's possible. We just haven't gotten there and it's hard, and it's just never come as a priority. But I realized the whole reason that they're locked is because of the inability to resolve the stupid data in the private data control. Guess what's not in interfaces? So, if you can build your APIs such that you use an interface to inherit into both sides and the implementation on your RT and the implementation on your desktop, you can bring them together and you can bridge them, the interface doesn't get locked. You can still add methods to it. You can still extend it. You can play with it. So that's a big one. It shouldn't be a big one. Classes shouldn't be locked when they're on multiple targets. I apologize. Someday.
You're absolved of your sins.
Huh? I'm absolved of my sins. Well, thank you. Trust me, I've done enough G development. I know what a pain it is. I've tripped over my own error there, and I'm like, yeah. All right, so that's what I wanted to teach you today. That is a short dive into one particular slice and giving you some background information so you know enough of how to use interfaces not to trip over them. This is some additional customer education options. First of all, National Instruments offers 2 cust-ed courses. The first is available now, is a fully revised for interfaces actor-oriented design. This is the actor framework. Any of you who have ever looked at the actor framework and balked at it because you like, oh, these abstract messages are a nightmare? They're gone. Interfaces completely eliminated the need for abstract messages. Gone. The horrible thing that was the biggest boat anchor dragging the actor framework down is eliminated. That course gets into all of the details. The earlier, the very first LabVIEW 00 course, or presentation that we did on interfaces back in April of 2020 that I linked at the start, Alan does a deeper dive into how it fixes the actor framework and how you can use interfaces. There's also a bunch of information already online about that. If you are an actor framework user, interfaces, go read up on them, and then you will weep tears of joy.
Stephen, for reasons having to do with some bugs in the actor framework tooling, you do need to go to LabVIEW 2020 SP1 to use interfaces with actor framework, and we're just recommending going to 2021.
Yeah. So the recommendation is go to 2020 SP1, not 2020, because we made it. We strengthened it and made it even nicer going in the SP1. The second is a revision coming to the 00 course that'll be available in Q3 that takes the 00 course and folds interfaces all the way through with new examples and shows you where to use them. There's on-demand training. I want to highlight this. These are little 15-minute courses on a huge range of topics that NI has been building over the course of the pandemic. There's various topics in here that relate to 00, and some of them do get into some interface things. In general, you should just know about that URL, and when you're trying to figure something out, there's a lot of really good content in there. It comes from NI, comes from the community, all sorts of different topics in there. So I want to highlight that. If you want to know all of the reasons why I did this or complain about my mistakes, just like I did for LabVIEW Object-Oriented Programming originally, this is the white paper, LabVIEW Interfaces, Decisions Behind the Design. It gets into all of the whys of, why did we pick this file extension? Why did we do this icon design? Where did these colors come from? All of that is in that document. There's a lot more content that can be in the LabVIEW help. The help for OO programming in LabVIEW is very extensive. I had a very good tech writer, just as we had for OO, help us with interfaces. And there are many customer presentations online at this point. We're 2 years out, and various people, some of them in this room, have made some very good things. Now, I don't know, how much time do I have left? 0. All right. Well, in that case, we're going to hold off on questions. You can talk to me afterwards, but I do want one last slide. And this is a little bit of a personal note. You all know me as Aristos Q. I have for almost 22 years worked at National Instruments, and I have been in LabVIEW R&D. And June 3rd will be my last day of work. I am switching to a different role, and I'm going to be joining out in the community. I figure I spent 2 decades building a language that I really love. I get to play in it now. So I'm going to be dropping the NI part, and I'm going to be a developer at SpaceX, working on their mission control software. So next year, I'll be out in the community, and posting questions to NI of, why the heck did you do that? Just like all of the rest of you get to do. So,
Are you going to complain about that guy that locked classes?
oh, you better believe it. Why haven't you fixed that yet? So, I want to just say it has been an incredible pleasure teaching all of you, helping out with your various projects, vicarious engineering, as I like to say it. I get involved in all of your projects. I'm pleased to have been able to help you with training and courses, and I hope to continue to see you online, just not in quite the same forum. There are other members of the LabVIEW R&D team that are going to start appearing online, and you'll see more of them as I take a step back. So thank you for 2 decades of being incredible customers, the best that anybody could ask for. Thanks.